Yeah. So if you promise to stay awake, Paulo,
I'll do my best.
Oh yeah, you said you might not be able to make it. Is that?
I mean, I'd say that also depends on you, right?
I will stay awake. Okay, I will start my talk now. So yeah, there's a famous story about someone who was had to give a course of lectures very early in the morning, and he had this terrible dream once where he dreamt that he fell asleep during his own lecture, and then he woke up, and it turned out that the dream was true. So hopefully that won't happen. No, I'm very wide awake, in fact. So I'd like to thank my grad students, Joe Moeller and Christian Williams, for doing a lot of the organizational work for this online seminar, which we call Applied Category Theory at UC Riverside. And here are some of the first talks. We've got a great lineup. I guess actually June 3rd may be the last of these spring talks, but there's also an open slot that we're trying to fill right before June 3rd. If you want to get more information about this, you can go to this URL down here and learn more. Let's see, sorry. So Christian Williams has also created this thing on Zulip, sort of a chat site, which he calls the Category Theory Community Server. And you can get there from the following URL. So when you first go there, you have to register, but then you can just go to a somewhat shorter URL, a different place. I mean, the same place, you don't need to register every time. And so that's really taken off. Maybe a bunch of you are already there. We're gonna talk about this seminar there right after the talk. And I guess, I'll ask Paulo a question. He's my token audience member. So the MIT people are also going to be doing chatting about their seminar on Zulip. Is that true?
Yeah, we started last week there, and we'll continue doing so. Yeah.
Yeah. So that's great that we have, and I hope more people who are interested in category theory do that. That is, have online seminars with discussion at this one location, so that more people can get to know each other. So I got interested in applied category theory because of climate change. I'd been interested in category theory beforehand, but the urgency of climate change made me want to move it into a somewhat more useful direction. And I've been struggling ever since to try to figure out how to reconcile my interest in beautiful mathematics with my desire to do something useful. And so it's great to see that a kind of applied category theory movement has taken off to try to grapple with that issue in many ways. So the problem with climate change, one problem with climate change is that it proceeds at such a slow incremental rate that it's hard for people to ever feel the urgency at any one moment to do anything serious about it. It's like the old parable of boiling a frog slowly in water. Apparently actual frogs are smart enough to hop out of the water when it gets hot, even if you slowly warm it up. But in the metaphor, they just never quite think it's too hot, and so they stay there and die. And it seems as if humans are more actually acting that way than the frogs are. So now in coronavirus, we have another great wake-up call, which maybe is giving people all the urgency they need to do things rapidly. And so one of the interesting spin-offs of that is this big rise in online seminars, which is exactly the sort, and conferences, which is exactly the sort of thing that we would like to deal with, to deal with climate change and cutting our carbon footprint. So I think that all conferences should have at least an online component, and the Applied Category Theory Conference at MIT, the this summer is going to be like that, forced that way now because of coronavirus. But I hope that even after, I'm going to tuck you down here, Paulo. I hope you don't mind being there. But if I don't see anybody when I'm giving a talk, it's just bizarre. It's like I'm lecturing to my laptop. So that's this conference, ACT 220, and talks are given by submitting papers, and I hope you all take your best papers and try to submit them to give a talk at this conference. And now you don't have to go anywhere. The talks will be distributed around the 24-hour clock in such a way that there will be some that occur when you're awake, no matter where you are. So that's a great new thing. Okay, so sorry, there's a bug that requires that I go into full screen mode twice to actually see the top of the screen. Now I want to make this stupid thing go away. Oh, I gotta make it just, I want it to go away. Okay, go away. No, it comes back. Every time some new person shows up, I guess this thing reasserts itself. So I'm going to give a talk about structured cospans and double categories, which is a framework for dealing with complex networks like the one in the picture here that was developed mostly of all by my grad student, Kenny Corser, with help from myself and also from Christina Vasilikopoulou. So throughout science and engineering, people use networks of many different kinds drawn as boxes connected by wires. So for example, in upper left there, you see an electrical circuit. In upper right, you see what's called a Petri net being used to describe a model of the HIV infection of white blood cells. We'll talk more about Petri nets. At lower left, you see a chemical reaction network of a sort used in biochemistry. And at lower right, you see what's called a signal flow diagram used in control theory, the branch of engineering where you try to design feedback loops to regulate processes such as industrial processes. And each discipline that uses pictures like this invents their own style of picture and argues about the correct use of these pictures and so on. And none of them typically think of these pictures as being mathematics. They think of the mathematics as, for example, the differential equations, which these pictures can be used to represent. That is some kind of semantic content of this syntax. But the pictures themselves, they think of as their own sort of personal way to talk about things, to actually understand them more easily. Of course, category theorists now know that these pictures are mathematical structures. Some of them are string diagrams in symmetric monoidal categories. And when I started noticing the wide use of these pictures in different subjects, some quite mathematical, I wanted to start blending the ideas of those subjects with the ideas of category theory to see if anything interesting could come of that. So the idea is that networks of some particular kind, so there are many kinds of networks and you have to fix a kind, but networks of some particular kind with specified inputs and outputs can be seen as morphisms in some particular symmetric monoidal category. So here I'm drawing maybe the simplest example where the network is a graph in the sense of category theory. That is a set of vertices, a set of edges, with every edge having a source and target vertex. So that black stuff is a graph, but we're equipping it with a little extra structure, which is that we have two sets, x and y, with functions from them to the set of vertices of our graph. And those are equipping this graph with inputs and outputs, and those allow us to see this graph with extra structure as a morphism in a category, because we could start gluing such pictures to each other along the inputs and outputs. So people use pictures like this and fancier versions to describe open systems. So the concept of open system is incredibly important. Loosely speaking, it's a system. Well, a system is an incredibly vague term. a system where stuff can flow in or out. So one role of the inputs and outputs is that stuff, meaning like electricity, matter, energy, people, can move in and out at those points, the inputs and outputs. And secondly, we can combine systems to form larger ones by composition, which means sticking these diagrams together at their inputs and outputs, and tensoring, which means setting them side by side. So I am advocating the use of describing these networks with inputs and outputs using cospans with extra structure. So this picture that I showed you just a minute ago, you can think of it as being a cospan of finite sets for starters. So that's the set X with 3 dots, the set Y with 1 dot, and the set S is the set of vertices of the graph there. So S has 4 elements. And the maps I and O map X and Y into the set of vertices of that graph. So far we've got here a cospan of finite sets, but it's crucially important that we don't just have the set of vertices here, we have a whole graph. So S is decorated with extra structure, namely the structure of a graph. It has edges as well. So Brendan Fong invented decorated cospans to try to make this intuition precise. So I gave Brendan a thesis problem of trying to make up a category of electrical circuits, and he took forever to do it. It was just so easy to do, but he was just like sitting on the problem for over a year. But then, like the goose that laid the golden egg, when he finally laid the egg, it was a solution to much more than the problem I gave him. It was a general formalism for describing open systems as cospans decorated with extra structure. So I forgave him for being so slow, because it was a great thesis. And so since then, various people have used decorated cospans to study many different kinds of networks. So the original paper that was sort of the motivating example was considering the example of electrical circuits. I just liked electrical circuits. Here's a circuit with just resistors, but our paper also considers other so-called passive components, such as transistors, not passive typically, such as capacitors and inductors. And so there are ways to think of those as decorated cospans, and there are ways to take a category of open electrical circuits and describe its behavior using a functor into another category. So we use the idea of Lever's functorial semantics to describe the behavior of networks. Then with my grad student Blake Pollard, Brendan and I worked on Markov processes, which are processes where you have a finite set of states, which are these things with circles, and then edges with numbers attached to them, labeling the probabilistic rate at which some entities can hop from one to the other. And in our particular case, we are studying so-called detailed balanced Markov processes, where each state, that is each circle, is also equipped with a number, which is a kind of equilibrium population. And then with Blake, we wrote another paper on reaction networks, which for the present purposes, you can think of as a synonym for Petri nets, or Petri nets with rates, which is what this picture shows here. So this picture is a Petri net, but the transitions, which are these blue things, have numbers attached to them. So these are a generalization of Markov processes where you can have several entities, like 2 entities, turn into one. Instead of just one entity hopping around the edges of a graph, you can have multiple entities turning into multiple entities. And I'm going to talk about those a lot more. That's going to be my favorite example for the purposes of this talk. But then Kenny Corser developed a simpler formalism that does many of the same things as decorated cospans. So we call this structured cospans. And so he and I recently finished a paper on structured cospans that's on the archive, and he's also finished his thesis, Open Systems, a Double Categorical Perspective which contains the same material, but also a lot more material. So that's what I want to talk about, structured cospans. And I'm going to try to keep the category theory down to a very low roar here. I'm tempted to give a very esoteric talk, for example, explaining the comparative advantages and disadvantages of decorated cospans and structured cospans, and the marvelous work that Christina and Kenny have done on that. But I don't think that that would be a good use of most of your time. I engage in my audience. I think I shouldn't let myself sink into those delicious details. But that's the great thing about being able to talk afterwards on Zulip. I'm very happy to talk about all that stuff. So what's a Petri net with rates exactly? Well, it's a diagram like this. So we have a set T of transitions, a set S of states, and each transition has a source and target, which is not a single state, but a formal linear combination of states, or I should say a formal sum of states. So N bracket S means linear combinations of elements of S with natural number coefficients. So those are finite formal sums. And then each transition also has a number attached to it called a rate constant, and that's a number between 0 and infinity. So, the elements of S are sometimes called species in chemistry, but in computer science, they're called places, and they are these yellow circles here. So you can think of them as places where little dots can sit. So you could have like 6 items of this type, and 3 of this, and 1 of that, for example, if you wanted, once we get going. That's not part of the Petri net structure itself, but that's what these yellow dots are going to be used for. The aqua squares are called transitions, and so far that's a Petri net, but then if you attach a positive real number to each transition, you get a Petri net with rates. And that will allow us to describe some dynamics for entities moving around from state to place in this Petri net. So since epidemiology is the science that everyone needs to be learning right now, I'll give an example from epidemiology. So I'll show you how, given a Petri net with rates, you can write down a system of differential equations that describes dynamics. And the example I'll give is the simplest model used in epidemiology called the SIR model, where those letters stand for susceptible, which is this. These are people sitting in this circle here are people who haven't caught the disease yet. I stands for infected, so these are people who are infected. And R stands for recovered, so people who've recovered from the disease are over here. And we have 2 transitions. This one here is called infection. In the process of infection in this simple model, a susceptible person and an infected person walk into a room, they shake hands, and now the susceptible person is now infected. So 2 infected people walk out the door, and now you have 1 more infected person than you had before, and 1 less susceptible. And then in this other transition, which is called recovery, a single infected person recovers and becomes recovered and perhaps immune to the disease. And in this particular model, they can't catch the disease again. You can make other models that are more complicated, where recovered people can, after a while, lose their immunity and become susceptible again. So you could just stick another transition in here to make the model fancier. And there are many variations of this idea that are in use.
Sorry, were questions supposed to be relegated to at the end, or can we ask in between?
Thanks. I was getting a little distracted. What I ideally would want would be for me to easily be able to see typed in questions and answer them. Right now, I'm having trouble managing the system so that I can easily see the chat and everything. Do you have a question?
Yeah, just R1. Does it represent, like if we normalize these R1 and R2, does it represent the probability of the person being infected after they shake hands, or?
No, that's a good question. Yeah, so speak regarding his meta question, why don't you, since I'm not doing a great job of this, why don't you do just what Arthur did and ask questions by demuting yourself, and try to keep them to be questions that are of a clarificatory nature, like he asked. And then at the end, I'll be glad to answer millions of kinds of questions. So no, yeah. So these numbers are not probabilities. They are numbers between 0 and infinity, and so they are what are called probabilistic rates. Or we're not really using anything stochastic in this particular approach. We could, but I'm not discussing that. So what you should think of is that when we write down these differential equations that describe the dynamics, we have a number of susceptible people, a number of infected people, and a number of recovered people that are functions of time. We're treating those as continuously varying things. So you could have like 3.7 people, but this is a useful approximation. They have large numbers of people. And so then what the role of R1 is that the rate at which susceptible people turn into infected people is proportional to the number of susceptible people times the number of infected people times this constant R1. Yeah, so it's called a rate constant. And of course the minus sign is because the susceptible people are going away when this occurs. One susceptible person leaves for each time this process occurs. And then they become infected people. So we see the same term here showing up with a plus sign for the time derivative of the number of infected people. And then this transition R2 is what's accounting for this term and this term. So this is the decrease of the number of infected people as time goes on, proportional to how many there are, and then the corresponding increase. So yeah, so you get these equations, and people have studied the heck out of these. They're not very complicated, luckily. And so this is a typical example solution to this set of differential equations. So here we start out with a lot of susceptible people, almost no infected people, but there have to be some. The graph is a little bit misleading. It looks like there are none, but there has to be some, or else no one would ever get sick in this model. And so initially the number of infected people starts to grow exponentially, approximately, but then as the number of people that have yet to get the disease drops, this growth rate starts slowing down. And then also people start, another reason why it starts slowing down is that people start recovering. And so they start, the number of recovered people starts increasing. So this is a typical solution to these differential equations. So that's a story in itself. So people have written whole books about Petri nets with rates and the differential equations that they give rise to, and how to deduce qualitative information about the solutions from the pictures of the Petri nets. But what I want to talk about is open Petri nets with rates, where you have inputs and outputs as well. And so you could just formally have a finite set of points here and a finite set of points here with maps to the set of places. And it doesn't, those maps, they don't need to be one-to-one or onto or anything. So you could have two going here, for example. I could have a place with no arrow pointing to it, although I didn't choose to do that. And so the idea is that you can imagine that this system that we're talking about is just part of a larger system where, for example, susceptible people could come in from some other part of the system and go into this part. So for example, this could be what's going on in one country, but there could be some other country over here, or two different countries over here, which have plane flights that drop off susceptible people into this country, or maybe drop off infected people into this country. And also, by the way, I should point out that although the arrows are pointing this way, we should imagine that entities can both enter at those points, but also leave at those points. So I'm sorry that my internet connection is unstable. I keep talking to it and it just does that. So when you have this situation, you get what's called an open Petri net with rates, and it gives rise to an equation called an open rate equation, which is the exact same set of differential equations we had before, but with some extra terms, one for each input or output. So these are also functions of time, and these are not determined by the differential equation. These are just arbitrary functions of time that would be in some sense determined by the external world in some way that we aren't modeling in this model here. And so the ones that are called inputs, we stick these functions of time into our equation, adding them with a plus sign, and the ones we call outputs, we stick them in adding with a minus sign, but that's just a bookkeeping device. All these functions could be either positive or negative functions. So if we wanted to have people flowing in from here, we would just make O1 be negative, and that would cancel this other minus sign. This bookkeeping of signs is mainly useful for when you start gluing these open Petri nets together to form larger open Petri nets, and you want something flowing out of one to be flowing into the other. So you have a little sign issue to deal with. So the kind of stuff that Blake and I showed was that there's a category of where the objects are finite sets and the morphisms are open Petri nets. And I'll say a bit more about that, a lot about that actually. But then what I won't say much more about is that what we use this for is functorial semantics. That is, there's a functor from that category to some other category where the morphisms are these open rate equations that I've been writing down. So you make a category where whose morphisms are the equations like this one down at the bottom of the page here. And we're composing morphisms means sticking together sets of equations to get new sets of equations. And since this is a functor, it means that you can compose Petri nets and then figure out the equation from them, or figure out the equations first and then stick them together and you get the same answer. So the process of getting a rate equation from an open Petri net is compositional. So that's the philosophy of this open system approach, is to describe the syntax of open systems using structured cospans, and to describe the semantics of it using functors to other symmetric monoidal categories. So I want to focus on the syntax, which is the structured cospans. So what's a structured cospan in general? So it's a very simple thing. So you have a functor from one category, which I'll call A, to another category, which I'll call X. And then a structured cospan is a cospan in X, that is a diagram in the category X, but of this shape here, but where the feet of the cospan, as they're called, these two objects here, are L of some objects in A. So it's sort of a diagram that sort of likes to live half in A and half in X, but formally it's all in X because we've applied L to these objects here. So you should think of A as a category of objects with less structure, like for example, just sets or finite sets would be a very common example. And X is a category of objects with more structure, for example, graphs or Petri nets or Petri nets with rates. And you should think of L typically as being a left adjoint. For example, you can think of a finite set as a graph with just vertices and no edges. And so this picture here is meant to hark back to our picture before of how I drew an open graph as being a graph with maps from two sets into it. But really, you turn those sets into graphs with no vertices and then map them into it via a map of graphs. So because L is a left adjoint, by the way, you could also pop this L over to the X and write it as an R of X on top here. When L is a left adjoint, you can rewrite the cospan in that way. So here's the basic theorem that is sort of a tool theorem. It's not supposed to be an exciting theorem, it's supposed to be just a tool kit. So suppose that A and X are categories with finite colimits. So that is push-outs and an initial object would be enough to get finite colimits. And suppose L is a left adjoint. Then you get a symmetric monoidal category where the morphisms are basically structured cospans. So the objects of your category will be objects of A, like this guy here and this guy here. And then a morphism from one object, like little a, to another object, little b, would be basically a structured cospan of this sort. But when I keep saying basically, what I mean is to say that, well, no, that's not quite true. It's really an isomorphism class of these things, because if you have ever done composing spans or cospans, you know that they don't compose associatively. They compose associatively up to isomorphism. So if you're trying to get a category out of them, you need to work with isomorphism classes of these things. So what do I mean isomorphism class? Well, it's just this. If I have one structured cospan and another one, they'd be isomorphic if there was an isomorphism in the category X between the so-called apex of this cospan and the apex of this cospan that makes these two triangles commute. So the idea is that, for example, if you've got an open graph, you might relabel the vertices or edges of your graph and get some other isomorphic graph, and that would count that would give you an isomorphism of this form, and so you'd get the same morphism in the category here. This is a niggly point which we'll return to. So here's how we compose two structured cospans. So if we have one and another, and the target of one matches the source of the next, we compose them by drawing them together and then taking a push out in the middle, which means sticking them together, sticking the objects X and Y together along the overlap L of A2. And then we get this new structured cospan as the composite. And that composition process is, as I said, associative up to isomorphism, which is why we use these isomorphism classes if we want a category. Then we can also tensor structured cospans, i.e. set them side by side using coproducts. Coproducts look like disjoint unions in the category of set, so that's how you set things side by side. So if I have one and another one, I can take the coproduct of these objects, the coproduct of these objects, the coproduct of these objects, and coproduct is functorial, so I can take the coproduct of these morphisms here, and I get a new cospan. However, in the definition of structured cospan, we want the feet of the cospan to be objects of the form L of something. So we really want a cospan whose feet look like this. But good news is that a left adjoint functor, which we're assuming now that L is a left adjoint, preserves coproducts up to isomorphism in a canonical way. So there will be a canonical isomorphism from here to here. So we can reinterpret this, or we can pad out this little diagram here with those isomorphisms, and we get a new structured cospan. So that's the mechanics of how we set two structured cospans side by side. So that's the category theory of it. Let me just illustrate it all in pictures because it's the simplest thing in the world. But I wanted to mention, I guess, first that this theorem applies to lots of examples. All the ones that I mentioned, basically open electrical circuits, Markov processes, and so on. And in all these examples, you've got these two categories, A and X, with finite colimits, A typically being the category of finite sets, X being a category of graphs or Petri nets or Markov processes or something, and some left adjoint functor. So let me show it to you for open Petri nets with rates. So first of all, we need that category called X, which will be the category of Petri nets with rates. So a Petri net with rates is a thing like this stuff up on top. If we've got another one down here, we could talk about a morphism from one to the other. So it will be a map sending transitions to transitions, and a map G sending places to places. Since taking finite sums is a functor, we can apply that functor to the map G and get a map from finite sums of elements of S to finite sums of elements of S prime. So we get these maps going down, and then we say that these maps F and G constitute a morphism in the category of open Petri nets if two squares commute, namely the square involving S and S prime commutes, and then so does the square involving T and T prime. So if you have a good category theory grad student and you ask them, if you tell them what an open Petri net is with no knowledge of what it means or why it is what it is, and you ask them what the right notion of morphism is between them, they should be able to guess this answer. If they can't guess this is the answer, then you send them back to category theory class where you learn how to guess things like this. So, sorry. I do not know how to move. Well, I can move it down here, and then it's equally irritating. Okay, go away. So there's a functor sending any Petri net with rates to its underlying set of places, those yellow circles. And that has a left adjoint, which sends any finite set to a Petri net with just those places and no transitions at all. So we do indeed have adjoint functors between our category with less structure, which I call A in the general example, and the category of things with more structure, which I would call X in the general case. So we're all set. We can do this. We can build structured cospans in this example, and so what we get are open Petri nets with rates. So A and B are these finite sets of the inputs and outputs. I see this little gizmo is annoying no matter where it is, huh? And if I were a computer scientist, I would no doubt know how to get rid of it, but I'm not. So I know that computer scientists don't even know how to do these things either. So there it is. That's an open Petri net with rates. That's our example. So let me just sort of show you a little bit about how you compose them. So here is a picture of two open Petri nets with rates, one going from the set A with 3 elements to set B. But because this slide isn't very wide, I drew the next one right next to it. So here's another open Petri net with rates going from B to a set C. And then when we do that push out to compose those structured cospans, we just stick these two guys together in the obvious way, identifying two places if they're both pointed to from the same purple dot, same element of the intermediate set B. So we just stick them together like that. So the idea is that you can build big complex models of systems by sticking together smaller ones. And the other way to stick things together is sort of more bland, setting them side by side. So if I have an open Petri net from A to B and one from A prime to B prime, I can take their co-product in this way, just setting them side by side. So all that category theoretic stuff I sketched in this example is just doing sort of the most obvious thing, which is you can stick things together end to end and attach them, or you can just set them next to each other. Now, that isomorphism class issue is actually important. You might actually want to use actual structured cospans as morphisms rather than isomorphism classes of them. Why would you want to? What does it matter? Well, sometimes you have an open Petri net that has isomorphisms from it to itself. So this Petri net has a symmetry that switches these two transitions here. So that's an isomorphism from this, that will give you an isomorphism from this structured cospan to itself. And what that means is that when we talk about isomorphism classes, it means that we're no longer able to talk about which transition is which. We've identified we've identified this one with its upside down version. So if you want to point to a specific place or transition in an open Petri net and say, you know, how many people are in this place, or what's the rate constant of this particular transition, you have to not use isomorphism classes. And so that means that the approach I've described so far is not really adequate. So then what we should do is not use a category, we should use a double category. So Mike Schulman has written a nice paper a long time ago on constructing symmetric monoidal bicategories from symmetric monoidal double categories, and together with Hansen, they have really enhanced that paper and made it much deeper, and recently put a new version, vastly improved version on the archive. So that's technology that for them was, well, it starts out being technology that says how you can get symmetric monoidal bicategories from symmetric monoidal double categories. But after studying this for a while, Kenny and I were convinced that actually symmetric monoidal double categories are simply better and more useful. And so I will only talk about them. So what's a double category? Well, roughly, it's a gizmo that has figures like this. So it has objects, just like a category does, but it has two kinds of arrows. It has vertical arrows, which I'll call vertical one morphisms, but then it has horizontal, well, at least in Mike's old work, he called them horizontal one cells. And those are things of a completely different nature than these vertical ones in general. And then they have squares or two morphisms that fill in the hole here, and various ways of composing these. So as you might expect, you can compose the horizontal arrows end to end, you can compose the vertical arrows end to end, and you can compose the squares. Well, if you think about it a minute, you should be able to compose those in two ways, setting them side by side horizontally, or else setting one on top of each other vertically. And various laws should hold. So the most exciting part is that the two morphisms can be composed both vertically and horizontally. And when you've got four of them, which are composable either vertically here and here or horizontally here and here, then there's a law called the interchange law that holds, which says that first you can compose these horizontally, then compose these horizontally, and then compose the results vertically, forming a big fat thing. Or you could have done it the other way around, first doing the vertical composition and then the horizontal composition, and you get the same answer. So that's the most exciting law of a double category. The kind of double categories we need in our work are what used to be called pseudo double categories. And what that means is that the vertical composition is associative on the nose and obeys the left and right unit laws on the nose, but the horizontal composition is more like what you see in a bicategory, that is, it's associative only up to an associator. And the unit laws hold only up to isomorphisms too, called uniters, which need to obey some identities, like the pentagon identity. I could say a lot more about this, but hastening on, the theorem is that you can build symmetric monoidal double categories of structured cospans under the exact same assumptions that we had before. So the assumptions of this theorem are exactly the same as last time. You have two different categories that have finite colimits, which allows you to stick things together, and a left adjoint from the first one to the second one. And now we're getting a symmetric monoidal double category out of it. So the objects are the same as before. They're objects of A. Now we have vertical one morphisms, which are just morphisms in A. So this F would be a vertical one morphism. But we've got horizontal one cells, and those are our structured cospans. So we had those before. So the new ingredient, the most new ingredient, well, the vertical morphisms are already a bit new, but the really new ingredient are these two morphisms, or squares, which are, you can think of them as being a map from one structured cospan to another structured cospan. So it's a commutative diagram of this form where you have morphisms F and G in the category A and a morphism H in the category X, making this sort of square commute. So that will allow us to talk about isomorphic structured cospans, but talk about that isomorphism as part of the structure of our setup, which is this double category, instead of having to work with isomorphism classes of structured cospans. So horizontal composition is defined using pushouts as before. So here I'm showing you how to compose the two guys at top, and we do that using a pushout. That's just like what we did before. But I'm also showing you how we compose the whole two morphism with another whole two morphism, and we get another whole two morphism like this. That's again done using pushout. Vertical composition is very straightforward because the vertical morphisms aren't these cospans, they're just arrows. So if I have a picture like this and then another picture down below, I just compose the arrows to get a bigger picture. The tensor product is using coproducts in both categories A and X. So if I have a square, like I'm drawing what happens to the two morphisms because that's the newest part. If I tensor this one and this one, I just stick plus signs everywhere and I get a new one. Here again, I'm using the fact that L preserves coproducts so that I could also rewrite this as L of B1 plus L of B1 prime if I wanted to, which we need to because that's what we get when we first take the coproduct of these two guys here. So that's roughly the idea. I should say that proving that this is a symmetric monoidal double category takes some work because although I've tried to whiz through them, the axioms, I didn't even tell you anything about the axioms of a symmetric monoidal double category. I told you about what a double category was, but I didn't say anything much about what it means for it to have tensor products and be symmetric monoidal. That was probably on purpose because it's a little complicated. And so proving this theorem takes some actual work. You could prove it just by writing down a big long list of axioms and checking them by checking lots of diagrams commute. There's nothing inherently difficult about it. It's just very tedious. But Kenny and I decided eventually to come up with a more high-powered approach that cuts through some of the tedium and replaces it with terrifying abstraction. So I guess you have a choice in category theory, right? You can either just check things and go crazy with boredom, or you can move to a higher level of abstraction and go crazy, but have more fun going crazy at a higher level. So I won't go into any of that proof. So these two morphisms, what do they do for you? Well, one thing they can do for you is if I got an open Petri net here and another open Petri net, there would be a two morphism from this one on top to this one on bottom. And it would just do the obvious thing. It would map these two guys down to this. It would map these two guys down to this, and it would map these down to this. So the idea is this could be like a complicated model where you have, for example, men and women, both of which have a random chance of, say, getting hit by a truck. Sorry to pick such a morbid example. But so with some rate, they turn into people that have been flattened out, right, like in a cartoon. And then you could say, well, that's an unnecessarily complicated model because what the men and what the women are doing is isomorphic. So you could map that open Petri net down to another one here where you just had a place representing people instead of two separate places for men and women. So you can use two morphisms for a more interesting purpose than I described before, as to actually describe simplification of models. But you can also use it to describe more embedding your model in a more complicated model. So for example, this open Petri net has a two morphism going to this one. You can see that it's sort of sitting inside this one where we've just put on an extra transition here. So there's a map from this one on top here to this one here. So this is sort of the opposite of simplifying a model. This is adding extra features to a model. So you could say like, well, maybe it could be that if you have two flattened people here, they have a chance of like joining together and then getting unflattened. I didn't pick the words for this example to be very realistic, but you get the point. I hope that you can get you can add extra features to models using two morphisms. So in summary, symmetric monoidal categories are good formalism for describing open systems. We treat those open systems as morphisms. That's a somewhat old point in a sense. Everyone who loves string diagrams has run into that point, I believe. The slightly new point is that symmetric monoidal double categories are what you want to describe open systems precisely, not just up to isomorphism. You need two morphisms to describe morphisms between open systems. And then, yeah, so, and what's good about that is that you can make more complex models or more simple models by, in a systematic way using two morphisms. And then the theorems show that structured cospans are a good formalism for building both of these types of things, symmetric monoidal categories and symmetric monoidal double categories. So I will stop here. Thank you very much. And I will try to switch to some more egalitarian format. So if anyone has a question, either type or talk, depending on what you feel comfortable with. Thanks, Alexander. Thanks, Christian. Thanks, Sarah. Thanks, Matt. Thanks, Josh. Thanks, Juan. I don't know you, Juan. Thanks, Joseph.
I'll come in with a question. Can you hear
Hi
me?
there.
Yeah. Hi. So my standard sort of question, we probably talked about this last year, but so many of the interesting sort of pseudo-double categories I know about, there's some relationship between the vertical and horizontal arrows. So given a vertical arrow, you get a pair of adjoint horizontal arrows.
Right.
So is that the case here? I mean, I can imagine you could just take some kind of empty Petri net. I mean, if you've got some morphism between them, do you get some sort of empty thing where you take one either way around or something?
Yes, that's right. I'm not even needed. I'm not even required to answer the question.
sorry.
It's fine.
Sorry.
It's fine. I can relax. I've been talking a lot. So yes. So what Simon's referring to is that in the, well, one aspect of what he's referring to is that in Mike Schulman's paper, Mike shows that you can get a symmetric monoidal bicategory from a symmetric monoidal double category if you have this extra feature that you can turn a vertical one morphism into a horizontal one pointing in either direction. And he nowadays Mike calls those fibrant double categories. And so yes, these structured cospan categories are all fibrant in that sense. And so the idea is that if you just have so they are isofibrant. All you really need is to be able to turn the vertical isomorphisms into horizontal things to get the symmetric monoidal bicategory. So that's all we are able to do. So if I have simply a map of finites, an isomorphism of finite sets, I can build an open Petri net where I use those two isomorphic sets as the input and output, and then the set of places in the middle is, well, either one of those two sets. And then use an identity morphism in one direction and that isomorphism in the other direction. And yeah, so it works that way. And that's important to us. Right, framed bicategories, Alexander, are Mike's old name for these things. And then that term was apparently universally reviled because framed means something else in topology, and he was introducing this for topology. So then he switched the term to fibrant. And I think there's another name for this exact same thing, which is a pro-arrow equipment.
Yeah.
What were you going to call it?
Equipment, yeah. Sometimes it's just equipment, yeah.
Yeah, just an equipment, yes.
Yeah, pro-arrow equipment.
So someone is asking, they saw that I needed that L preserve coproducts, but I did not need that it was a left adjoint. And it's certainly true that I don't need the full force of it being a left adjoint. So in the more sharp version of the theorem, where we whittle down the assumptions to the bare minimum, I think all you need is that the category A has finite coproducts, the category X has finite colimits, and that L preserves finite coproducts. But I decided that if I stated a theorem with assumptions like that everyone would hate it. And in every case where I've actually used the theorem, these slightly more powerful assumptions are true. And yes, we are going to use the Zulip chat. In fact, some of you can go off and start chatting on Zulip right now. And that may be what we'll all do in a while. But since I like seeing actual people, it's nice to do a little bit of this.
Yes. I have a remark. Oh, sorry.
Whoever. Who's speaking?
Okay.
Lee is speaking. Oh, no, Zenobi is speaking.
Okay. So I have a remark. It seems you said that the double symmetric monoidal
justifies that we can consider spans not just up to isomorphism, but actually they do much more because your vertical morphisms are any, right?
Right.
So it's much more than not just up to isomorphism.
That's true.
A relationship between different systems. Yeah.
Yes, right. So the initial reason for us wanting to introduce them was simply that working with things up to isomorphism gets annoying if you want to actually point at something and say this part. But you're right. We get much more out of it and much more useful things out of working with morphisms that aren't isomorphisms between structured cospans.
Beautiful, these vertical things. Just what's needed in many applications. Because we need to relate such things, right?
Yes, that's right. Yeah. You're often doing things like taking a model of some sort, like did you draw some kind of network and saying, whoops, I forgot some nodes. I need to stick in some extra nodes or things like that. Yeah.
This is what engineers do. They say do refinement. You start.
Yeah, they have names for that, like model refinement. And then they also have another name, I think, for model reduction, where you're collapsing many parts down to one. So
whatever you want. Yeah. Okay. Thank you.
Yeah. Question?
Yes. I'm sorry. Yeah, go ahead and ask your question. I'm going to go ahead and ask. I'm going to answer some other type of question in this while you're doing it. Sorry, if you don't mind, but yeah.
So, John, reaction to a line of thinking that is stimulated by your opening remarks about your intersection of interest and particularly what you were just mentioning about the power of embedding. So here's my concept, and I wonder what your reaction is. I've been interested in for a long time in trying to mathematically try to get a grasp on, the power of metaphor in thinking, in organizational behavior, not just as some kind of abstract notion, but something very practical. One of my favorite books, I'm sure you're familiar with, is Metaphor. And, that has no categorical foundation or whatever, but it makes the strong point that the way our dynamics of thought works is deeply metaphorical. And, Sloan's management school, lots of management schools, look at simulations as ways of getting a grasp on the way we think about problems. But again, it's sort of notional. So here's my concept. Might what you just articulated by way of the power of embeddings, for example, be a pathway into a more deeply mathematical understanding and mathematicization, formalization of metaphor? And, it would relate to the questions that you posed of political issues and urgent issues related to simulation. So I'm asking, do you think this line of reasoning that these double categories might give us a pathway and open systems together into mathematization of metaphor, which is such a powerful notion? Your reaction? Do you think
I don't see how. I don't think much about trying to mathematize metaphors, so I wouldn't necessarily know. I don't see right off the bat any way that this helps, but since I haven't really even tried it, I haven't really even tried formalizing the concept of metaphor. I don't know what
one chapter says, here gives an example, argument is war. So argumentation has a Toolman, all kinds of structure of argumentation. War has its dynamics.
Right.
These are not just words, these are dynamic systems. And insofar as we can kind of start to understand and get a mathematical grasp on how they modulate each other, this is not just sort of a minor interest in public policy, in simulations. That's where I'm coming from. But you're saying you don't necessarily think there's a pathway there.
Well, if you think about that, you could think that you have like two models of things. Like you can imagine a complicated model of what a war is and a complicated model of what an argument is. These models would have apparently a bunch of things in common that would allow you to say this in argument is like that in war, this is like that. But then also a lot of things that don't match. And so I think one of the tricky features here is trying to describe imperfect maps between structures, maps that aren't the kind that mathematicians love, where everything here is perfectly sent over to something here, but something where like, it doesn't really quite work, but it's like good enough. So that's I think the difficult and really important issue, how to deal with.
We would need semantic filters, so to speak, so that, you know, you kind of suppress.
So I will just say one thing, which is something that surprised me and interested me, which is that there was some nice work being shown at the last Applied Category Theory conference on categories where you can, let's see, how does it work? Categories where you can try to compose morphisms that don't quite match. So categories with some notions of distance built into them in ways that you can like sort of try to get things to work that don't quite work. So I think all sorts of ways of blending metrics-based ideas with mathematics to describe approximately approximate structures is good. Okay. I should give someone else a chance at a question if they want. Maybe everyone's run off to Zulip or to the coffee machine. Oh, here's a question. Someone's apologizing for a bad question. Okay. Is there any useful connection to operads? This is incredibly related to operads. Yeah. So, I mean, what can I say? So I don't know the beautiful theorem that should exist, which says something like when you have a structured cospan category, there is some operad that describes the ways of sticking together structured cospans to get other structured cospans. There will be some theorem like that. The connection between categories and operads is so beautiful that we should never think of it as being some kind of a conflict between two warring formalisms. So just especially when you bring in typed operads or colored operads, there is an operad whose algebras are categories. There's an operad whose algebras are monoidal categories. There's an operad whose algebras are symmetric monoidal categories. There's an operad whose algebras are compact closed categories, and so on. And so one thing you see from what I just said there is that they are acting at slightly different levels. There are different kinds of categories, and then different operads whose algebras are that whole kind of categories. So an operad sort of describes a collection of ways you can stick things together, and in some kind of category, like compact closed category, you have a certain selection of ways you can stick morphisms together. And so like structured cospan double categories, is there an operad that's just sort of suited to describing what you can do in those? It might be a 2 operad actually, because it's a higher level. I haven't worked that out, but there's bound to be something good about that.
So I've got a question.
Sure.
Which is, so this whole line of work broadly is we've got better and better ways to sort of take various sorts of processes represented as open networks and describe them really nicely and the ways in which they compose and their morphisms and stuff, right? And that sort of where we've gotten, and then you've also got these representation theorems that go with that to sort of take their semantics, you said. So so what's the sort of future work? Like assuming all of that just gets nailed down rock solid and you've got this toolkit, but it's, things that one does on a chalkboard or a set of slides, right? Is the work more in the software direction, or, you'd want to be able to sort of have some theorems that let you relate the morphisms to the semantics or something, right? Like how do we apply the descriptions of applied things?
Yeah, that's a great question. That'll have lots of different answers, I think, depending on which way different people want to go. So I'll mention two, I guess. So since I'm a mathematician, where I would like to go would be to study particular kinds of systems, for example, these open Petri nets with rates, and prove theorems about their dynamics, the qualitative properties of their dynamics that really depend on the openness. So these open Petri nets with rates are really commonly used in mathematical chemistry, and there are some really beautiful theorems about how the dynamics of chemical reactions depends on the topology of the network, and lets you get a handle on like how systems could either always approach an equilibrium state or have multiple equilibria or oscillatory behavior. Let you determine that without having to actually solve the darn differential equations. And those are so far for closed Petri nets with rates, without things flowing in or out. So someone is asking more about that stuff. So I want to generalize that to the open situation, generalize those results to the open situation, and to try to find some really new kinds of results that only work in the open case. So I mentioned that for open Petri nets with rates, but that would apply to sort of any one of these particular kinds of models that you describe. So that's one style of answer. That's sort of the style of answer for the mathematicians or the chemists or whoever they are. I think there should also be another style of answer having to do with, say, people wanting to build software tools for dealing with these models. So hopefully this mathematics would help at least guide you in dreaming up software for designing models. I mean, there's already a lot of modeling software for Petri nets and for lots of other things. So this is further away from my ken, so I can't really say like, okay, using the fact that I've got a symmetric monoidal double category, I know that your software should do blah de blah and blah de blah. But I think that like getting the mathematics nailed down should really actually help people design flexible modeling software. It's just not my job, my field, unfortunately. So my advice is very vague in that direction.
So my follow-up is then, I guess, well, then you need what a general notion of topology is. If, someone hands me, here's a, structured cospan or something, can I just hit it with, homology, right? Or whatever, right? That would be sort of the dream. And is there any work that sort of has started to sketch in that direction or something, or?
Sorry, I was a little distracted. So what do we do? What kind of things are you wanting to do by hitting it with homology?
Saying, you would like to use this formalism and, be able to sort of generalize certain topological theorems about things it represents, right? So the question is, well, do you have an idea of how to, quote, find topology in this very general setting that you've created yet?
Yeah, I do, in fact. So the existing work on Petri nets uses topology. It's fairly simple for topologists because these things are just graphs, which in topologists treat graphs as very, very simple kind of topological spaces. But it's still, but you get non-trivial results in chemistry out of doing this, so it's definitely worthwhile.
Right.
And all of that should be able to be generalized to the open case. So, so I'll throw out a buzzword of homology. So relative homology is for when you have a space, but then it has some kind of boundary or border region, which you could take here to be the inputs and outputs. So yeah, I think there's stuff to do there, definitely. And I should just start doing it now that I'm done with some other projects. So I just gave a link to my book on Petri nets and some theorems connecting topology to dynamics for Petri nets. And as Nathaniel pointed out, the deficiency zero theorem is a classic result whose conclusion is that some class of Petri nets will give you dynamics that has a unique attractive equilibrium point, roughly speaking. And so this book of mine includes a proof of that theorem. It's more like a textbook. What should we do? Any more questions? I'm starting to get curious to know what if anything is going on Zulip. But I'm also perfectly happy to entertain physical questions, if that's what the word for this is.
What about slides? Will they be posted somewhere?
Yeah, they already are, in fact.
Oh, okay.
And so I will, yes, so they're available. And I'm going to try to drop a link to them in the chat window over here, if that helps. So you can email, what? That's not it. The wrong link. Nope, that's not it. Is there any way on that? Sorry, okay, wait a minute. Okay, Vinay gave the right link. Yeah, I don't know how to delete my message. That previous link is the link to the Zulip thing, so I didn't do the cut and paste right. I'd say, since nobody's bursting in to ask more questions, hi, Joachim, I see you there. I'm going to go grab some coffee, more coffee, and then meet people on Zulip for even more disembodied form of conversation. So thanks very much for all attending this first seminar in the series, and I hope to see you all in various ways.
Thank you.
Okay, great. Bye. Bye.